So here we are, the day before spring, wishful thinking, Thanksgiving break. And you have an extended break for this class. There's going to be no class on the Tuesday when you come back from break. I did that because we're going to finish up logistic regression. And so the choice was to start new material that you weren't going to be tested on or just give you a break here rather than the day after the exam. So your exam is here. Usually I give you no class right after the exam. If you prefer, that's fine, but then we'd have to start new material that you're not going to be tested on, and people don't generally like that. So if you prefer to have a no class there, that's okay. I can give you a survey about it. Just a show of hands. How many people would prefer to just start new material that's not going to be on exam 3 and have no class here? Raise your hand. How many people prefer this schedule? All right. Oh, unanimous. All right. So that's what we're going to do. So then you'll have no class here. So we'll have finished everything up. The practice exam, everything, you can start studying if you want, but I doubt people will. You'll have the homework that's due right here. You can finish right after class, maybe at the end of class. It won't be a long class. And then we're going to have a review for the exam, and if we have anything left to do to catch up on, we can do that here. And then your exam is that Monday, and then we'll have 3 classes. We'll have 2 on non-parametric statistics, and then we can have a final review too. So that's what it looks like, and your exam is right after reading day on one of these 2 days, and you're going to have the same, you can sign up for either one. There'll be a conflict. If you prefer to take one or the other, whichever class you're in, there'll be a conflict sign up. And we'll be taking it with the other class. Yeah? What did you say? Homework 21 is due. Oh, I see. Homework 21 is going to be due right after the exam. Yeah, because there's going to... Homework 20. Homework 20 is not here. Thank you. I got to erase that. Thank you. There's not going to be any homework due then. I could move this 19 to there if you prefer. Yeah, I could just move this over to there since we're not having a class. Sure. So this will be moved over to here, and yeah, I'll update that. Thank you very much. So you'll just have one homework due here, and it's the day before we meet. Any other questions? All right. So let's start the lecture then, and go to the document camera and turn to page 185 in your books. It's chapter 39. Okay, so this is the last chapter on logistic regression, and we're set to do inference now. To extrapolate from our sample statistics to wider population parameters. Now, inference for logistic regression is nearly identical to inference for regular regression that you've already learned about. So this is going to be pretty easy for you guys. Basically, in both cases, the first thing we do is we test whether any of the slopes in our model are significant. So remember the general form, it's in log odds. So we have it's linear in log odds. So we have the log odds equation, and then we have these slopes, coefficients in front of our predictor variables. And that's the intercept. But as usual, what we first do is we do this overall hypothesis test, significance test, that says the null hypothesis being that all these slopes, betas in the population, this is what we get in our sample, but all these coefficients in front of our predictor variables in the population are 0. So in other words, our best estimate for the log odds would just be the average percentage of people. Like in our example is the log odds of, we're trying to predict the probability of getting into medical school based on some predictor variables. So this intercept would just be the percentage of people who got into medical school in our sample. The usual. All right? And then the alternative hypothesis is at least one of these is not 0. There's something to our model. And then, as usual, we're going to investigate if the overall significance test rejects the null, then we know there's something here. And then we're going to look at these individual slopes and do z-tests on them, just like we did before, and build confidence intervals around them, too. So in ordinary regression, remember we've been using either a chi-square test or an f-test. For the smaller samples, we use an f-test for this overall null hypothesis. But in logistic regression, we're never going to use an f-test. Why? Because we're predicting counts. You know, basically, did somebody get in or did they not get in to medical school? So the probability distribution, including the standard deviation, is determined directly from the predicted counts, as it is for a chi-square test, as it is for anything where we are predicting percentages. Because when we predict a percentage, the mean, let's say the mean of people getting into medical school is 0.8, let's say, or it wasn't, it was like 0.4. Well, then that's tied to the standard deviation, because when you know the mean, when you know, let's say the mean was 40%, well, then you know the standard deviation is what? P times 1 minus P, and then take the square root of that. So it'd be 0.4 times 0.6, 0.24, and the square root of that, which is very close to 0.5. So we don't, so unlike F or T test, which we're using, remember they estimate the standard deviation from variation, not from the predicted mean itself. That's why we do them. When we don't know the standard deviation and we have of the population, we just know it of the sample, and we're trying to estimate it of the larger population, and we have a small sample, and it's not a very good estimate. And then we have to deal with all those degrees of freedom, etc. But we don't have to do that when we're dealing with counts. We never do F or T tests. So that's how we're going to be. That's logistic regression. We'll never use them either. So our tests are going to be chi-squared, or likelihood-based analogies, or analogs of chi-squared. The statistic we're going to be used with large N will be distributed as a chi-square statistic. So we're not going to use F or T-like distributions at all. All right, that's the idea. And then the degrees of freedom in our model is just going to be just like the chi-square degrees of freedom. It's the number of parameters in the model minus 1, the number of slopes in the model. Remember, the number of parameters in the model is all these B's, and then the degrees of freedom for the chi-square is the number of parameters minus 1. All right? So then, if we do get some significance in the overall model, then to test, and then we're going to look at the individual slopes. And remember, in ordinary regression, we used either a z-test or a t-test for small samples. But in logistic regression, we always use the z-test, or z-squared, chi-squared with 1 degree of freedom, or a likelihood version of it. All right? So here's we saw this on the previous page. that when we did this multiple regression, we got this log odds equation right here. Right here, the log odds was equal to, it's right here. And now we're going to first test the overall model and then test these individual slopes. And here, you can see they're both significant. We're jumping ahead. There's a z-test here for the individual slopes right here. And there's an overall chi-square test. So let's look at this more carefully. So first, let's start with this overall test. And it looks very significant here. Huge chi-square with only 2 degrees of freedom. Remember, chi-square is when the null is true. In other words, when these slopes are 0, the chi-square curve has a mean of equal to its degrees of freedom. It's equal to, so it would be equal to 2. The degrees of freedom is the number of parameters minus 1, same thing as the number of predictor variables in your model. And the mean would be 2, and that's so much bigger than 2, which is why we get this very small p-value. Much less than that. It's actually much less. It's just this program doesn't go out to so many digits. We can look at the p-value in a moment. But now what's this right here? This is analogous to our ANOVA table. It looks very similar. It's breaking up the total, what's called the deviance, which plays the role of the sum of squares errors, or sum of squares total, into 2 pieces, our model and our error. And this is sort of the logistic regression version of our ANOVA table. Maybe we should look at this a little bit further, what's going on here. Okay, so let's turn the page and read about this. Okay, so I'm just going to, I'm just going to give you a sort of intuitive explanation here. If you want to read a lot more about this in detail, you should go to, I can show you where, because I bet a lot of you do want to read a lot more. We'll go through this and then I'll show you where you can read a lot more about it. Okay? All right, so the main difference between the ordinary and logistic regression is how we're estimating those betas. We said before that we usually minimize the sum of the squared residuals, the errors around we're trying to get the best fitting linear equation, and we minimize the sum of the squares errors. But here, instead of doing that, we are going to try to use a likelihood method of doing it, which is maximizing the likelihood of getting our sample data. Those two things are the same in linear regression, but they're not the same when you do logistic regression because it's impossible to do that. Basically, remember that each one of our points, every one of our points, whatever its x value, it's going to result in either a 0, meaning failure, or like didn't get into med school, or whatever, it's a 0. We're predicting a yes or no outcome. So it's either going to be 0 or 1, right? So then when we do the log odds, each log odds is either log odds, so that's success over failure, or failure over success. So it's going to be either 0 over 1, log of 0 over 1, or log of 1 over 0. So that's either negative infinity or positive infinity. So you can't really minimize the squared error of the predicted logs of odds because we'd be fitting a bunch of infinities. That's the basic problem. So we could do, like I showed you, we could bin them. Like in the beginning, we could look at intervals and look at within each interval, we could say the percentage of people who got into med school, right? We could do that. And but lots of times we don't even have data in some of those intervals. And also what the betas we get will depend on how we actually lump them together, what intervals we choose. So then we could, if we do that, so basically if we break the data up into intervals like I showed you before, and instead of just having y's as 0 or 1, we'll say the percentage of people who got into medical school or who succeeded with that interval would be our prediction. We could do that. We could minimize that. And that would do a good job of fitting near in the middle of our data, but it would do a very bad job of fitting at the ends, at the extremes. And often you really, like in our medical school data, we want to calculate odds for people who are at the extremes, who are very, and so it does a terrible job of doing that, and maximum likelihood estimates is sensitive to rare events and picks up the parameters throughout the entire range of the data. So that's why we want to do that. So what are we doing instead of minimizing the sum of the squared residuals? Instead, we're maximizing the likelihood of getting the data that we want. But the easiest way to do that is through a log likelihood. And since our probabilities are between 0 and 1, then our log likelihood would be negative, right? And so instead of doing that, so instead of trying to maximize, we would mean getting the least negative. So instead of doing that, maybe I didn't write that down here, but minimizing the deviance. Okay, so what do? Instead, we maximize -2 times the log likelihood. But it's still minimizing the deviance. And so deviance plays the same role in logistic regression as the sum of squares in ordinary regression. So if you look at the analysis of deviance table on the previous page, it looks very much like our ANOVA table. So maybe people who want to read more about how exactly this is done should read, and if you're in the R course right now, the 390, you should be reading this. So you should read lesson 13. This is the lesson that's due after break. But anybody who's interested, I recommend read lesson 13. How do we get to that? How do you get to that on the lessons page when you go to our regular website? If you want to go directly to it, you just say go.illinois.edu, and then instead of stat 200, you can get to it through there. You'd say stat 390. I'll show you what it looks like. So you can just get to it if you want to. I recommend, especially if you're going to be a stats major, you should. All right, so let's go to, I can show you where it is. All right, so, and those of you who might want, you might want to take the independent study next semester. So, how come this, I thought I put the, oh, there it is. So if you want to take it next semester, you can register. Right, there's the CRN for it. All right, so if you go to the lessons page right here, and then you go to the lesson right after break. Right here, this gives a really nice introduction to likelihood methods. And so I recommend reading that. And then what we just talked about, you'll recognize these are our formulas that we're using. And so we're going to maximize the log likelihood. And here's some examples, and what we just talked about is down here. We are going to this is what we're dealing with. We're going to try to max right here. It's called the deviance, and it's -2 times the log likelihood. And so that's what we're doing here. So we get this r squared that's slightly different than our r squared that we have. But I don't want to go through all this now because it would take too long. But it's the same idea. This r squared that we get is going to play the same role. It's the sum of squares of the model over the sum. It's analogous to that. And I can show you that. And so if you want to read about this, you can. It's up to you. But you're not going to be tested on it. And I found that if I talk a lot about things that people aren't going to be tested on, nobody learns it. So if you want to learn it, you can go here. But the intuitive idea is this. And the rest is just the math of it. All right, so let's go back here and see what we're doing. And so if we look over here, we see that we get this r squared, and as I just said, it's not the same r squared we've been talking about, but it is 29.33 here divided by 75.79. So it does match up with this same, the structure of it is very similar to our ANOVA table. All right? But what's different is, like, you're not going to calculate chi-squared statistic by saying r squared over 1 minus r squared times n. See, this is is matching up with your chi-square statistic there. And this statistic right here is distributed as a chi-square statistic with the degrees of freedom p minus 1. All right? This r squared is called the McFadden's r squared. You don't need to know that. We're just going to refer to it as r squared. All right? And so here's r, and if you square that, you're going to get r squared, and this is how it matches up to a chi-square statistic. And here is what we got. These are z-tests we do on the individual slope. All right, so let's look at this, and we'll just treat it as a usual chi-squared, because it is. All right, so now we're going to say, okay, so our null is that both betas in this model, all the betas in the model, so both, there's two of them, slopes in the population, we're using these Greek letters for that, are equal to 0. And the alternative is our usual, that no, at least one of the slopes in the population is not equal to 0. And then you can see we got this chi-square statistic way up here. First of all, also we're going to compare, and this will just be given to you. We're going to be comparing our chi-square statistic, and that's huge, 29.33, to some critical value. As usual, to some critical value we can compare it to, chi-squared critical value, at how many degrees of freedom? What are we going to put in there? Well, the degrees of freedom is equal to, remember, the degrees of freedom is equal to the number of parameters minus 1, so it's going to be 3 minus 1, which is equal to 2. So degrees of freedom equal to 2. That's what that says. And then we have to say it's some significance level. Well, this is a huge, 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 big chi-square. Remember, it's going the shape of the curve. We can look at it in a minute, but just to get a rough picture, you should know it's always positive. And that's going to be way, 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 way out on the tail, because that's 29.33, and when the null is true, the chi-square statistic, its mean, you should know, is its degrees of freedom, which is 2. So it's going to look like, 2 would be about here, let's say, and if 2's about there, then we're going to have like this long, long thing. I can't draw it, but it keeps decreasing and getting closer and closer down there, so to 0. So we're going to have a very, very small, because our chi-square statistic is what? 29.33. That's our chi-squared. And so this little area beyond that is very, very tiny. All right, but if we didn't have, let's say we just had our usual table, what would we do? For example, on an exam, you'd say, okay, chi-square with 2 degrees of freedom. And I guess with the furthest out, you would choose, we know that the p-value is going to be less than 0.1% because our chi-square stat is bigger than that, than 13.82. So we could conclude that that compared to the chi-square stat at p equals 0.1%, and that was 13.82. So that's at what? 0.1%, or alpha equals 0.001. And since our chi-square stat is so much bigger than that, we can say that the p-value is less than 0.1%. Does that make sense to everyone? Since 29.33 is greater than 13.82, our p-value is less than 0.1%. To draw the picture, we'd say that, okay, our p-value is greater than that, and that means that 13.82%, wherever that is, 13.82%, that's our critical value, that means that from here on in is 0.1%. I didn't draw that really well because that looks a lot bigger. You wouldn't be able to see it if I drew it accurately. But from here on out, that whole thing would be 0. From, all that would be, just trying to get a different color. Here, this whole thing. It looks really big, but it's just 0.1%. Okay, so that's p equals 0.1% there. And ours is our chi-square is so much bigger than that, so our p-value is less. Our p-value is less than 0.1%. Much less. Does that make sense? Sorry, it's not too pretty, but you get the idea. Hey, why don't we look on the computer and you can see it better? Okay, so let's go to the computer and, whoops. And let's go back to stat 200 to our p-value calculator and to the chi-square, and we have 2 degrees of freedom here, and we have a 29.33. So you can see it's out of the plotting range. It's very, very small. Okay? And I tried to draw it so you can see it's really very tiny. Any questions on that? Okay, so now we'll go back to, so now we can test whether the individual slopes are significant. All right, So let's do that. And to test whether the individual slopes are significant, we don't never do t-tests for the reasons I explained. We just do z-tests. So let's state the null and the alternative. So let's start with the gender slope. And what would be our null hypothesis? Sorry, I got to get to the document camera. Our null hypothesis would be what? That the beta in the population for gender is equal to 0. Remember, we have this equation. We have this log odds equation, the log of our odds, p over 1 minus p, p over 1 minus p, is equal to negative 17 plus this slope here that we got in our, we got this right here in our sample. Yeah, we could get in our sample, but what we're saying is that in the whole population, it's really 0. We have a pretty small sample here. So this was our slope for gender, and it was coded males equals 0, females equals 1 for that. And then we had this slope for the biological science score. And that was our predicted log odds. Okay, and that's our hypothesis. Now, what do you think our null? Do you think it should be two-sided or one directional or not? We really didn't know. In fact, we didn't know whether males or females were going to be favored. In fact, I thought probably males would be. So I think the alternative should be two-sided because we didn't know. We didn't state ahead of time. At least I didn't. If I did, I would have been wrong. Okay? So it looks like that. And then we're just going to do our usual. Z equals our observed slope minus our expected slope over some standard error for the slope, like usual. And our observed slope's that. Our expected under the null is 0. And the standard error for the slope was given to us. And it will be, because it's complicated to figure out. So it's that right here. And you can see they got this z and this p. We can get the same thing. We'll get the same thing. So here is the standard error. So let's write it down here. So the standard error is 0.8579. And when we divide those, we get exactly what they did. The program did. So that is our z. And then, so what are we going to do? So we can just look at, the p-value calculator, or we can just, might as well just refresh and do this simple thing. So we know that as a z-score, we'd expect 0. Also as a slope, we'd expect 0. And all we're trying to do is match up where is this? When the null is true, we expect a slope of 0. We got a slope of 2.015. Well, we didn't know where that was until we said this is the typical standard sampling error of the slope. And now we see it's very, very significant. It's way out there. So it's, as a z-score, it's 2.348. As a slope, it's 2.015. And we want it, it's two-sided. So our p-value will be the area of both tails between, so it's symmetrical, so it's going to be a two-tailed z-test because we didn't know which direction it was going to go in. And if let's just say we had just on an exam, we couldn't do anything but use the table, so let's just make sure. So what do we have? We have 2.345. We can just round it up to 98.12 in the middle. So we have 98.12, which would then leave on the two tails together. So our p-value would be just 100% minus 98.12, which is 1.88%, the two tails together. Okay? So our conclusion would be to reject the null. If we set the usual significance at, well, let's say we set it at alpha equals 0.05, we'd certainly reject the null and conclude that this slope was significant for gender. All right, that's the idea. And let's see, we got that p-value, but we rounded up. Well, it should be very close to that. Let's look. Yeah, it is 1.89. Okay, so that's good. And now let's do, we can do the same thing. We don't have to go through it, but we could do the same thing. Let's just see if we wanted to test the other slope, it would be exactly the same thing. Let's just set it up. So now we'd say the beta for the biological science score is equal to 0. That's the null hypothesis, that nothing's going on. That's a ridiculous null hypothesis. It doesn't matter what you get on your biological science score, it's not going to affect your acceptance to medical school. That's crazy. But so our alternative would certainly be one-sided. In this case, we'd know that we'd expect to see what? A positive. Don't you think the higher your biological science score, the greater your log odds of getting into medical school are? Right? You wouldn't think the lower. Otherwise, why would you even study for those MCATs or anything? Right? Okay, so yeah, so of course it's going to be greater than 0 because we know that the higher the biological science score, the greater the acceptance to medical school. All right, that's what we think. Of course, it could change. Maybe it could be the opposite, controlling for things. I still don't think so. No. All right, so then we do the same thing, but this time we just do a one-sided test, right? So do you want me to go through it or not? No, I don't think we need to. But let's see. If we did do a one-sided test, I'll just tell you what I got when I did it. I got half of this here because these tests are always two-sided. So this just, you have to just be careful. These programs, generally the default is to return two-sided tests, so you would just cut that in half if you said ahead of time what your hypothesis test was. Okay? All right, now let's do, before we even turn the page, let's do an iClicker. Now that we know that we're rejecting the null at 5%, and the null is at the slope 0, what would that be equivalent to in terms of a 95% confidence interval? So let's think about that and do an iClicker. So we just saw that the two-sided p-value for the gender slope in the log odds equation was less than 5%, right? It was 1.88%. So we can conclude that a 95% confidence interval for that gender slope in the log odds equation, what? It's just what we just did, but I'm just matching it up to a 95% confidence interval. Okay, I'll just give you 1 minute and then we will stop it. And let's see what see what you said. The answer is what? B. Yes, good. All right. So this does not include 0. All right. So let's go back to the document camera for a minute. And let's look at it. And it does not include 0. It's the same thing. Because that's what we just, remember, here's the log odds equation. The log odds, again, was this. And we're talking about this gender slope here. And we rejected the null that it's equal to 0, which is so we know that 0 is not included inside this confidence interval for the slope. Here's the picture is this. So a 95% confidence interval is between z equals negative, will be a little more exact, negative 1.96 instead of negative 2, and positive 1.96 here. All right. And so this right here, this area is 2.5%, and that's 2.5%. And it did not, our interval here did not include 0. And here's our picture. It looked like that. So certainly it didn't, it's outside the interval that would include 0. So if we went 1.96, we're at 2.348. If we went 1.96 this way, we wouldn't include 0 in that way. See? We get down to 1.96 times our standard error would get us down to what? 1.96 times our standard error would get us down to somewhere right there. That's what we did here. You take, how is this computed? We build confidence intervals the usual way. A 95% confidence interval, the way this was calculated, was what? We can do it right. We just said, it says it right here. We just say 1.96 times the standard error and subtract it from the slope. And that's what you would get. And it doesn't include 0. So now we did that, and what if we want to build confidence intervals? We get these endpoints, and same with the biological score, that also did not, biological science score did not include 0. And now, and that's our usual way, the confidence intervals did not include 0, so that's equivalent to a two-sided z-test giving a p-value of less than 5%. Right there, that's the same thing, that's what we just said. And then to build confidence intervals for the odds ratio, we're going to do the two-step process. We're going to find the endpoints for the slope, well, they're already given to us, and then exponentiate each. So we can do that. I mean, they're given to us right here, but I could, let's say they weren't. So you'd say the 95% confidence interval for the slope is going to be equal to what? Well, the lower endpoint will be 2.0, the sample slope, minus, usually we say 2, but we're being a little more exact here, times the standard error for the slope. That would be the lower endpoint, and that takes us down to here. And then the upper endpoint would be the same thing, 2.015 plus 1.960 times your standard error. And that takes us up to there. Okay? So we can just copy that down. So that's 0.3331 up to 3.696. That's the same thing as that. So now what do? Then we exponentiate the endpoints. So, oops, step 2 is a 95% confidence interval for the odds ratio for gender. Remember what the odds ratio for gender is? The odds ratio for gender is just e to the slope. And last time we saw that was about 7.5. So now to build confidence intervals around there, remember it's not going to be symmetrical around 7.5. That's going to be the geometric mean, as you can see. You see, we can't add and subtract this little standard error. That goes with the log odds. So we're just exponentiating each end. So our lower end point is, and our upper end point is that. And when I did that, I got 1.4 to 40.29. And you can see that 7.5 is not the mean of those two, but it is the geometric mean. So you could check that. You could check that the square root of 1.4 times 40.29, ask yourself, is that 7.5? And it is. I mean, with a rounding error, you can see, look what you did here. It has to be. I mean, it's just arithmetic. It'll just take a second. All I'm saying is the odds ratio, right, is e to the 2.015. So when I take the square root of the endpoints, and how did I get them? By exponentiating e to the 2.015 minus 1.96 times that standard error, right? 1.96, and the standard error is 0.8579, and then I'm multiplying it by the same thing plus. Sorry if I'm boring everybody, but plus that 1.96 times 0.8579, and you can see that and that cancel out, and all we're saying is this is the square root of it times itself. So, of course, it's the geometric mean. So you should get within rounding error. All right, so any questions on that? All right, let's go on then. So that means what? We're 95% sure that the odds for females getting into med school in this model are between what? 1.4 to 40.2.9 higher than the odds for males getting in. And if we did the same thing, we can do this more quickly because now we know what we're doing. So for the biologicals, just do it in 2 steps. You have to do this step first, and then you just exponentiate that, those 2 endpoints. So we know that the 95% confidence interval for the slope, we have it written right there, is 0.7525 to 2.567, does not include 0. Right? If it did, then we couldn't have rejected the null at the 5% level. Oh, for this one, what would it be equivalent to? We did a one-sided for this one. So this we'd have to match it up to a one-sided was 5% on one side. So that would be a 90% confidence interval, not a 95%. So we'd have smaller limit, smaller bars. Okay, we'd have 90% would be like 1.65 instead of 1.96 here. All right, so now for the odds ratio, we're just saying e to that. Sorry to be so tedious. We're going to get out of here very soon. And e to the 2.567. And I got 2.12 to 13.03. And then you would check, again, you would check that your actual odds ratio, what is your actual odds ratio? Your actual odds ratio is e to the 1.66, and that is 5.26. So you would just to check your arithmetic, like on an exam, I would just make sure you didn't make a mistake, times 13.03. The square root of that is at about 5.26. And it is. All right, so let's just do the last question as an iClicker question. Here, let's just do this last one as an iClicker. So let's go here. And, all right. So the 95% confidence interval for the gender slope in the log odds equation does not include 0. That's what we just said. So we can include the 95% confidence interval for the odds ratio for gender what? Okay, just pick one of those. All right, I'm going to stop it now and let's see what you said. Which one is it? Oh, you weren't just sure, but does not include 1, but most people got it. All right, so let's look at that. Okay, so remember, we're saying biological science score matters, right? It's not a 50-50 odds. It's not a 1-to-1 odds, 50. So, whoops, I wrote this wrong. So I said, if the odds are 1-to-1, then the log odds are 0. Sorry. Let's get rid of that. I should have said 0. Let's write it down here, and then we can go. So let's go back to the document camera. Sorry, that's wrong, what I wrote there. So I said, okay, so this is 1 right here. And so what I wanted to say was, look, we know biological science score matters. So we know that the odds aren't 1-to-1. And that means the log odds do not include 0. And remember, when we say the probability is equal to a 50-50 shot, that's the same thing as saying the odds is equal to, it's the same thing as saying the odds equals what? 1-to-1. And it's the same thing as the log odds equals 0. So when we say our log odds is not equal to 0, that means our odds ratio does not include 1, and that means our probability is not a 50-50 thing here. Does that make sense? Okay. So I think you can read this all on your own because it's, I just want, aren't you itchy to go home for break? How many people are leaving? How many people? I'm leaving really soon. You're not? Well, I just want you to have a great fall break, and I'll see you on Thursday when you get back.